Thank you. So the organizers asked me to give an introduction to functionals of Green's functions. And I will concentrate on the conceptual questions. That is, why are we doing what we are doing and how are we doing it? And this work is very much based on collaborations and discussions with members of the Palaiseau Theoretical Spectroscopy Group and in the more broader network of theoreticians, the European Theoretical Spectroscopy Facility. I have a lot of different aspects and points that I would like to discuss with you. And essentially, these are the questions of the motivation for our work, a link to density functional theory. It's always good to compare to density functional theory. There are many parallels. Reasons for choices we make, and of course, approximation strategies. And there are a number of strategies that I would like to discuss more in detail. So what we always want to calculate in physics are observables. These are expectation values, and in a many-body system, there are expectation values with a many-body wave function in the ground state, for example. So what we need is the operator that gives us the kind of observable we want to calculate. And at zero temperature and for fixed particle number, the many-body ground state wave function of the system that contains the information about the system we are looking at. So this is a very simple expression. It's just an integral, a huge integral, and it gives us, for fixed observables, the value of the observables given the many-body ground state wave function. So it is a functional of the observable as a functional of the wave function. This is not the only possibility. It's easier to see that if we go beyond zero temperature. So we go to a grand canonical ensemble here, and we have temperature in the prefactor beta, and we have the chemical potential with particle number. And that is the partition function. So we have the statistical weights, and we use these weights to calculate a weighted average over expectation values. This weighted average can be written as a trace. So that means that the explicit many-body eigenstates disappear in the expression. And we're left with something where we see the operator of the observable and the Hamiltonian. The Hamiltonian, as usual, that has kinetic energy and Coulomb interaction, and it has in particular the external potential. And this is the system characteristic ingredient in the Hamiltonian if we think that the Coulomb interaction is universal, same for every system, and if we think that the kinetic energy is the same expression for every system. So with this, since our expression for the observable only depended on the operator for the observable and the Hamiltonian for given system is given by its external potential, then this means that actually we have written the observable as a functional of the external potential given the chemical potential or particle number. So that means that we know the observable as a functional of a quantity, the external potential, that is much simpler than the full many-body wave function. However, the expression to calculate, although we know it, is very complex. We have a trace, so we have huge integrals and we have huge sums. And these are not easy to evaluate because the operators do not commute in general. And so we didn't really simplify the problem, although we could have thought that we have simplified it. So you see what we did. We sort of changed strategy. We moved from a simple expression, in principle simple expression, the functional of the many-body wave function, which is a very complicated function, to a more complex functional of a much simpler function. In both cases, this is not easy to evaluate. And the question could be, are there still other possibilities? Maybe a sort of compromise with a still reasonably simple function, but maybe a functional that is easier to evaluate. And of course, we know a possible answer. And this can be inspired by looking at an observable that is a observable linked to a local one-body operator. And if we go back to this wave function expression and we evaluate it for a local one-body operator and do the integrals, we can see that many things integrate out. And at the end, of course, as you know, our observable is actually an integral with the one-body density. So we need only the one-body density to get an explicit expression of the observable as a functional of the density. This is not true for other observables, of course, but density functional theory tells us that in principle, every observable of ground state properties is a functional of the density, and evaluated at the ground state density, it will give us the correct result. So we have now three possibilities, and we can make a comparison. Calculating observables of the wave function as a functional of the wave function means that we use an explicitly known functional, just the integral. The input to this functional, the wave function, is a highly complex object. It is difficult to calculate, and by the way, also difficult to store. And also the integral itself, although it's easy to write down, is very difficult to calculate. It's a multidimensional integral. If we choose to write the observable as a functional of the external potential, again, we have an explicitly known functional. The input, the external potential, is simple. It is known, we don't have to calculate it. And the problem is only that the functional is exceedingly difficult to evaluate. In the case of density functionals, the explicit functional is known for a local one-body operator, but most often for other observables, it is unknown. The input is simple, it's density, but we don't know it a priori. We have to calculate it. And the first expression that we have is that it is an expectation value in the many-body ground state. So that means, again, it is very difficult to calculate. And moreover, we don't know the explicit functionals or even implicit functionals for many observables, so we cannot even say how difficult they will be to evaluate. This sounds terrible, but to be fair with density functional theory, we must say that there is a solution to at least one of these problems. And that is the fact that we have a variational principle. And the energy in density functional theory can be written as a variational functional of the density. And so if we minimize the energy with respect to this density, we will find the ground state density of the system. So here the quantity Q plays the role of the density, and we have the strategy that we take our observable here, the energy, as a functional of this Q. We minimize, we get the ground state value for this quantity, so the density. And with this value, we can then calculate either the energy itself, which is just the value taken with this ground state density, or if we know the functionals, other observables, by using this density as input. So, moreover, having a variational functional is, of course, an advantage for the energy itself. So if you are interested in the energy, variational means that you are in a region where the result is a quite flat curve, so close to the minimum. If you have a density that is not perfect, you can still expect that you have a reasonably good result, of course, if you have a good functional. Now, this is not true for other observables. They are not necessarily variational. In general, they are not. And so the function is not flat, and you need a quite good density maybe to get a good value for the observable. And that means if you get your density from a minimization of the energy, that you would need a quite good functional for the energy to get a quite good density. So we have a little bit reformulated the problems of DFT. We still have the fact that the explicit functional for the observable is most often unknown. The input is, of course, still simple, and now we know how to calculate it. But to calculate it, we need knowledge of the energy as a functional of the density. And finally, we still don't know how difficult functionals will be to evaluate because we don't know them.
We can say, so many people say that density functional theory leads to very computationally efficient schemes. As you see, actually what we should say is, because we don't know the functionals, we don't know the exact explicit functionals, we hope that density functional theory helps us to find approximations which will lead to efficient calculations for the density and total energy and maybe other observables. And of course, we should also, to be fair, say that the fact that we know the Hartree energy explicitly in terms of the density, of course, is a big help in density functional theory. Now, this is so a quite good choice, density functional theory. We know the success, okay? But we might be interested in other observables. And what we also know from density functional theory is that the problem already starts when we are interested in the kinetic energy. So if we do the same thing as before, we start with the wave function, we calculate expectation value, and we try to reduce the problem by integrating out everything we don't need. We come, of course, to the fact that the kinetic energy is an explicit functional of the one-body density matrix. So this suggests that the one-body density matrix is actually a good quantity with which to build functionals, and people do this in reduced density matrix functional theory. So there are some observables that are particularly easy to express in terms of the density matrix. It's a little bit more complex than the density. It's non-local, but it's still a very good choice. And you have the same problems as before to find other observables in terms of the density matrix, of course. Now, what we are interested in, especially in the group, is spectroscopy. So spectroscopy, which brings a system from the ground state to some excited state, for example, because you shine light on it. And then the kind of things that you need are expectation values of some operator, some dipole operator, which stands for the light, which might be frequency dependent, of course. And then you have your many-body wave functions in the ground state, and you go to some excited state. And if you work this out, you would have phase factors, which are energy differences between ground and excited states. And you would have matrix elements that give you the transition amplitudes. And this kind of things is actually what you find in the object we're interested in today, namely Green's functions. So if you build Green's functions, and here we are interested in the one-body Green's function in particular, and I just write the greater part, you find exactly these energy differences between the ground state, or here this is the grand canonical ensemble, so any two many-body states, with which, if we are at zero temperature and fixed particle number, one would be the ground state and the other one would be some excited state. And you have the transition amplitudes that in the case of the one-body Green's function are the Dyson amplitudes, which I give here. So this is the kind of things we need to have a direct access to spectroscopy. And this is why we originally work with Green's functions. So Green's functions, like the density matrix, is again a sort of compromise, building functionals of the Green's function between building functionals of the density, which is particularly simple, and functionals of the full many-body wave function, which limits us to quite simple systems, and the Green's function sort of in between. Now we have the same problem as in density functional theory, namely the Green's function itself, which will be the input to our functionals, is an expectation value in the many-body ground state, which we don't know, which we don't want to calculate. So again, in principle, we don't know the input to our functionals. And then, of course, we would like to have a strategy that is similar to DFT, namely to say, can we have something that is variational such that we can find the Green's function? Now, the Green's function, let me also just remind you that the diagonal of the Green's function in space and time is the density, and the diagonal of the Green's function in time, but not in space, is the density matrix. Okay, so the one-body Green's function being containing the density, but being a little bit more complicated, and containing the density matrix, but being a little bit more complicated, of course, contains explicitly the expectation values that you can calculate with the density or the density matrix, namely the expectation value of one-body operators, be it local or non-local, because it contains also the density matrix. So these are really simple expressions in terms of the Green's function, the one-body Green's function. You would think that for the total energy, this is not possible because, of course, you have the Coulomb interaction, which links two particles, but it can be done. The total energy can be formulated in terms of the one-body Green's function. And the probably most well-known formula is the Galitsky-Migdal formula. So you see, you have the total energy, which is an integral of the one-body Green's function. At the end, you will take the diagonal, and here you have the one-body part of your Hamiltonian and the time derivative. So you can say, wonderful, okay, we do have the total energy as a functional of the Green's function. The problem is that this is an explicit functional, but it is not variational. And you can easily imagine why this is so. It cannot be variational because here, nowhere is written what the interaction is. So it means that this expression hides information. You would lose the information if you just minimize straightforwardly this expression. The fact is that you can also write other functionals, other energy functionals of the one-body Green's function, many different energy functionals of the one-body Green's function, actually. And I have written here the grand potential, so I move away from the zero temperature fixed particle number formalism, but never mind. So one functional that is maybe here particularly interesting is the so-called Klein Functional. I give you the reference here. So it has a part that is not specified here that is actually containing all the exchange correlation effects. And then it has some traces over known parts, and these contain the non-interacting part and the kinetic energy. So this is another functional of the one-body Green's function. Now you would say, but only one of them can be correct, right? The fact is that you have a function of a function, so you can change the input function and you get a new result. And so if we just take the function here and on our input function, the Green's function here, and your energy, you will have the Galitsky-Migdal functional here that is not a minimum at the correct Green's function. This is my correct Green's function for my system, say. So here the Galitsky-Migdal is not a minimum. And you have the Klein functional that is different from the Galitsky-Migdal functional, except at the physical solution, where the two functionals are the same. And here the Klein functional is a minimum. And you can have many other functionals that are similarly different everywhere except at the physical solution. For example, the Luttinger-Ward functional. So actually, I was wrong. Sorry, I expressed myself wrongly. The Klein functional doesn't have to be a minimum. It has an extremum. So it can be a saddle point, for example. It is flat. Okay, I designed a minimum, but it is not shown to be a minimum. But it's flat, so the derivative is zero, so it's variational. And so you could, for example, think that you can evaluate it with a Green's function that is not exactly the solution, and you would still get a quite good result, for example, independent particle Green's function. And by the way, I put a note here, when you use the GW approximation, I will come to this in a minute, then your Klein functional gives actually the RPA formulation of density functional theory. Okay, so this Klein functional contains this function phi, this functional phi, which, as I said, contains exchange correlation effects, and this is still something that we have to approximate. Okay, and this is how you come to the GW approximation, because you have to approximate this part. Okay, so Klein functional is a variational functional, not necessarily a minimum at the correct solution. But let's say in the Green's functional framework, we have something like in DFT, we have a variational energy functional such that we can find, in principle, the Green's function without using the many-body wave functions. Okay, And if you do formally this variational ansatz, then you will find that the self-energy, which plays the role of the Kohn-Sham exchange correlation potential, is the variation of this phi functional with respect to the Green's function, like the exchange correlation potential of Kohn-Sham is the variation of the exchange correlation energy with respect to the density. And you will find that the Green's function obeys the Dyson equation, with here the non-interacting Green's function, and this plays the role of the Kohn-Sham equations that can also be formulated as a Dyson equation. So now we have a strict analog to DFT. And you can really compare the two. So you have Kohn-Sham DFT and our Green's function framework, where you have the self-energy instead of the exchange correlation potential. Okay, so let's say we have a framework to find the Green's function. We either approximate this energy functional, the phi functional, or we approximate the self-energy that plays the role of the exchange correlation potential. And then with this Green's function, we can calculate other observables. For example, the kinetic energy. Because for the kinetic energy, we said we only need the density matrix. Density matrix is contained in the one-body Green's function. So we have an explicit functional for the kinetic energy. And what is very important for us, we have an explicit functional for the spectral function. The spectral function that is proportional to the imaginary part of our Green's function in frequency space. So the spectral function is what you measure if you do, for example, photo emission. So you come with a photon, you kick an electron out, you measure its kinetic energy, and this gives you an idea of something that you might interpret as the energy of this electron that it had in your material. And in a non-interacting picture, your spectral function would be, like I draw here on the left, it would be sharp peaks, and every peak would correspond to an energy level that you have in your solid. So for example, you have a solid, you have a band structure, so you get, as a function of momentum, you would have sharp peaks. This would give you the band structure, and equally for the unoccupied states. In a many-body system, it's not so easy. Your spectral functions are much more complicated. So you have peaks that are still sort of looking like the one particle, single particle peaks here, but they are weakened, they are broadened, they can even completely disappear. And you have additional structure like satellites here that come from the fact that when you do your excitation, when you kick out the electron from the system, you can excite other excitations in the system like plasmons, and so you get additional structure in your spectral function. And all this is contained in this one-body Green's function, and you have an explicit expression to get the spectral function from the one-body Green's function. And this is really a major reason to use functionals of Green's functions, because you have an explicit functional for the spectral function. So if we now compare our options, I have thrown the external potential option out just because I think that we essentially don't use it. Of course, we can do potential functionals, but let's not talk about it. So we say for the many-body wave function, we have 3 difficult points, and they're all linked to the fact that this wave function is difficult to get, difficult to calculate, difficult to store, and difficult to use. In the case of density functional, we run into the problem that most functionals are unknown, and we don't know how difficult they will be to evaluate. And in the case of the Green's function functionals, this is very similar to density functional theory. Simply, our input is a little more complicated, and we have more observables that we know explicitly as functional of the one-body Green's function. So what is then really our task when we are working in this business? We have to find the Green's function. And this means either we find the variational functional of the energy, and this means the exchange correlation part, or we directly approximate the self-energy. Second, we have to solve the corresponding Dyson equation and calculate G, or we have to find some other approximation for the Green's function from outside. That's also a possibility. Then, if we do not know the observable as a function of the Green's function, we have to find the functional expression, maybe approximate. And then we have to, of course, plug the Green's function into this expression and evaluate our observable. It's interesting to note that the observables we are usually looking at, for which we have an explicit expression, they're all linear in the one-body Green's function, the ones we know exactly. That's actually interesting. Same for the density, I would say. Okay, so if we look at that, so we have some observables that we know explicitly and others that we do not know. But what is sure is that we are looking for approximations that are simple. Because as I have shown you before, we actually know the exact results, right? I mean, we know the exact observables in terms of the many-body wave function or in terms of the external potential. So we are not looking for exact results here. We are looking for approximations. And for these approximations to be competitive with the exact result, they must be simple. And this holds probably for all many-body theory. All what we do is we are heading for potentially simple approximations. And when we say that density functional theory is computationally simple, this is only because we have simple approximations.
Lucia, excuse
Yes?
me, may I? Because somebody asked, I think, an interesting question comparing green functions and DFT. So this is a question by Christoph Friedrich. So I read the question. The green function analog of the Kohn-Sham auxiliary system is actually the real system if the self-energy were exact, whereas this is not true for the Kohn-Sham system, even if the exchange correlation potential were exact. Is this correct?
No, so we are talking about auxiliary systems, okay? And if we have the Kohn-Sham system, this Kohn-Sham potential gives you, in principle, correctly only the density, right? Now, when we go to our, let's say, Dyson equation, our Dyson equation with the self-energy gives us, in principle, correctly our one-body Green's function. You do not know the full many-body wave function starting from this Dyson equation. Only if you know the Green's function as a functional of whatsoever time-dependent, non-local, external potential, then you could take derivatives and get also other observables, okay? Mm-hmm. Yeah. But as it stands, no, we cannot reconstruct the full many-body wave function. We just get more information correctly than from the Kohn-Sham equation.
Yeah. Okay, thank you.
Thanks for the question. Okay, so let me just see. So we agree we have to find approximation, and of course, an infinite number of approximations around. And I would like to focus on strategies. And these are my favorite strategies, okay? And you might have other favorite strategies, and we can talk about this later. One is the use of exact constraints. One is the use of generating functional equations. One is perturbation theory, and perturbation theory always starts from something, and this is what I call a model, and so one is the use of models. So let's look at the use of exact constraints. Exact constraints are actually very, very much used in the framework of density functional theory. And you have, for example, this, just to take one, Klein Functional, which uses 17 exact constraints. And this is very successful. In the framework of Green's functional theory, we talk a little bit less about exact constraints to construct functionals. So I feel, although there are attempts, I just put you one example. But there's one constraint that we actually explicitly or implicitly often use, and this is linked to symmetries, which are linked to conservation laws. And here's particle number, total momentum, total angular number, and total energy. And I guess that Robert will talk more about this. And it's the fact that when you approximate your phi functional following diagrammatic rules, that means that you don't break any symmetry that you need to build this functional. You have rules that are really reflecting the two-body nature of the interaction. And if you take the self-energy as a functional derivative of this phi functional, and then with this you build your Dyson equation and solve it self-consistently, all these conservation laws are fulfilled. So getting your self-energy from as a functional derivative of such a functional is actually using an exact constraint. And there's a lot of work around, for example, from Robert, but also from many others here. The problem is that if you apply this exact constraint and you want to go beyond first order approximations, such as GW, you will see that this violates other exact constraints. And in particular, might give you negative spectral functions. This has already been observed by Karl Olof Almblad many years ago and has now been worked out by the work I cite here and subsequent works. And there are also fixes to it. But I just take this as an example. And here is a reference, if you're interested, that also talks about the problem to fulfill several exact constraints at the same time. It's an example for the fact that you cannot have everything unless you have the exact solution. So when you're heading for an approximation and you use exact constraints, you must choose what is the most important constraint for the application you're looking at. What is more important, being conserving or having positive spectral functions? This you have to decide, okay? Second approximation strategy, the use of generating functional equations. So what do I mean by this? You can start, for example, from the equation of motion for the one-body Green's function, which means that you take its first time derivative. And when you do this, you will find that the equation of motion contains the two-body Green's function. And if you write the equation of motion of the two-body Green's function, you get three-body Green's function and so on. Okay, so if you want to close this, you have to use a trick. And I think the use of this trick started probably with the work of Schwinger in the 50s. And you can find more about this, for example, in a nice book of Karanov and Baim. And you can also find more things in a book that we have written a few years ago, and which has a lot of things based actually on these equations. So the trick is to say, I apply a little perturbation to my system. This perturbation is an external potential U that depends on space, spin, and time. And with such little perturbation, I can create response-like objects, like a two-body Green's function is a response-like object, you see. And with this, I can replace the two-body Green's function and get a functional derivative of my one-body Green's function with respect to this perturbation. And then I have an equation that is a functional differential equation, and that looks like a closed equation. There is no two-body quantity around anymore. So the GU is the Green's function in presence of this external potential. And when ideally you have solved this equation, then at the end you would set this little perturbation to 0 and you would get your original solution you're heading for. So VH is the Hartree potential. Okay. So that's an equation that is really extremely interesting. And we have been working on this for many years with many people. I think most of them are actually in the audience here, and I hope I didn't forget anyone. Just a note, density functional theory and reduced density matrix functional theory can also be expressed with all these kind of functional equations. Not this differential equation, but the generating functionals. So let's say we have a functional differential equation, and now we have to do something with it. And maybe the first question you could ask is, why don't we just solve it, right? Why don't we just solve this differential equation? It doesn't look so difficult after all. So one problem is that to solve it, you run into the difficulty that a differential equation has many, many solutions, and you have to pick the good one. And you could say, well, I could solve it with an ansatz that respects my boundary conditions, for example. Okay. And then you find one problem with Green's functions that is actually, I think, interesting, and this is why I bring it up. If you want to make an ansatz or parameterize your Green's function, you should know what a Green's function is. Meaning that a Green's function, which depends on space, spin, and time, is not simply any function of two space, spin, and time objects. Or to be more precise, not any function of two space, spin, and time arguments is a one-body Green's function stemming from a static local potential. And you can see this easily. And this just because the density is the diagonal of the Green's function. So if you have an external potential, the external potential, a particle number and chemical potential gives you the ground state many-body wave function. And there's a one-to-one relation. And there's a one-to-one relation with the density. And the density is the diagonal of the one-body Green's function. So if you take the one-body Green's function, a good one, and you take its diagonal, you get the density. This must correspond to one given external potential. If you now change one off-diagonal element, you would still have the same density because you only change the off-diagonal element, not the diagonal. So you would get the same density, so it would correspond to the same external potential. But the same external potential cannot give you two different Green's functions because the external potential gives you the ground state wave function, which gives you the Green's function. So this is not possible. So most of these two space, spin, and time non-local objects are not one-body Green's functions stemming from a local potential. And actually, even if you look at the non-interacting Green's function, you can see that this is not trivial. So this is one big problem that we have. We talk much less about this definition of the domain of the Green's function as we do, for example, in density matrix functional theory. So since we didn't really manage to solve this equation, except for some things that I can talk about later if I have the time, what you, of course, usually do when you have this, you rather sort of iterate or make approximations wherever you can do it. And in this case, well, what is really disturbing here to solve the equation is this functional derivative. So you would approximate the functional derivative. So if you just use the fact that the functional derivative is a response-like object, or if you do it mathematically formally, you can write the derivative of the Green's function in terms of the derivative of an inverse Green's function. Okay, this is just straightforward mathematics. It's like deriving 1 over x. And then you derive the inverse Green's function. And if you now make an approximation and you think that the inverse Green's function only depends on this external potential and not on the Hartree potential and not on the exchange correlations of energy, then you get just two independent one-body Green's function for this functional derivative. And this is like an RPA response approximation, right? It's like the random phase approximation. And if you plug this in, you would immediately see that what you get is the Fock self-energy. So this is the Hartree-Fock equation. Now, this is not good enough. What we usually do is we actually do not work with the bare interaction. What we usually do is we use chain rule. So we say, okay, the external potential plus the Hartree potential, we call it the total classical potential. Okay, so we can here write the total classical potential. And then we insert here in this derivative a chain rule with respect to the total classical potential. Okay. The derivative of the total classical potential with respect to the external potential is nothing else but the inverse dielectric function, the screening. And so you are screening the bare Coulomb interaction, and so you get the screened Coulomb interaction here. And you are left with the derivative of the Green's function with respect to the total classical potential. Now you can do the same trick as here and do the same approximation. And it is better now, because now in this derivative, you also take into account the Hartree potential and not only the external potential. And this is how you get the GW approximation. You get it exactly like you get the Hartree-Fock, but you work with the total classical, so the screened potential, instead of working with the bare potential. And of course, you can do this further and further. You can add more and more things in your potential, and you will get more and more involved effective interactions, closer. Actually, you would get Green's functions closer to the exact one. Okay. What you can also do is to use this trick of rewriting the functional derivative in terms of the functional derivative of the inverse Green's function. use this trick directly in the equation in a general form without doing any approximation, and then you can identify actually that here you have a self-energy. So you have a all this is now exact, and here you have a self-energy term, and this is the exact Dyson equation with the exact self-energy. And then you can approximate the self-energy. And for example, if you think of the famous Hedin's equations, they are based on this equation, a little bit written differently, and from this equation you can derive Hedin's equations very, very easily. Okay, I will maybe, let me see.
Lucia, yeah.
Yeah.
Can I, before you move on, because there's an interesting question by Thomas Duguay about the representability problem you talked about. So yes. Is there lots of work in the literature? Are people really working on that, trying to define proper domains of representability, or as it's done in density metrics, functional theory, for example?
I would say not in our community. Okay. So I have asked several people in our community. This would not mean that outside our community, there couldn't be very interesting work, which I'm not aware of. Mm-hmm. And we should not forget that this kind of equations is the equations from field theory, very much applied in fields like quantum chromodynamics. There is a lot of work on solving this kind of equations. For example, in quantum chromodynamics, and I have promised myself to look through the literature, and we might find more interesting references there.
Okay. Okay. Thank you.
But of course, maybe some people here in the audience are aware of that, and that would be interesting. Yeah. Okay, I will now skip a few things. So this is working with self-energies. I would like to mention that you are not forced to work with self-energies. You can also work with other ways of doing things, for example, cumulant expansions, and we have some work on this. And if you are interested on this way of using the functional differential equations to get the ordinary cumulant equation and also more advanced cumulant approximations, for example, in this work, I can explain this separately. Okay. Perturbation theory is a very important topic, so I rather spend a few words on that one. So I wanted to show you some common approximations with Hartree-Fock and GW, but more in general, of course, when you have such an equation, you would say, well, let's just iterate it. So let's just, like, for example, solve this first part here. I set this to 0. I get a new Green's function. I plug it in. I get a new derivative. I iterate, tuck, 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 and I get a series. And this is actually how you get the perturbation series. Because, of course, each time you make a new iteration, you have another Coulomb interaction coming. So if you iterate this original equation, you get perturbation theory Feynman diagrams in terms of the bare Coulomb interaction. If you iterate this one, which is also exact in terms of the classical potential and the screen Coulomb interaction, you get another perturbation series in terms of the screen interaction. And you must, of course, be careful. The screen interaction itself depends on the external potential. So when you do the derivatives, you also have to derive the screen interaction. But in this way, you get correctly another perturbation series in terms of the screen interaction. And people working in extended systems would rather prefer this one because it has screening built in, which is very important in extended systems. Okay. This also tells you that there is not something like the perturbation expansion. There are many different possible perturbation expansions, okay? And you have to decide in what you expand. And then we have to ask ourselves how good this is. Because to be very honest, we always talk about our perturbation expansions, but most of us stop at first order. And if we are really, 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 really enthusiastic, we go to second order. But we never go to very high order. And we don't really know what's happening at very high order. Well, we should know. And I will also be short on this one, but I would like to advertise this. Many of the problems of this perturbation series are actually built coded in the structure of this equation. For example, the fact that the interaction is the prefactor of this derivative. So the details that make this equation so complicated, for example, the fact that it depends on two space, spin, and time objects integrated over and so on, they are actually not so important for what's going on. So if you want to get an idea of what's going on in perturbation theory, you can use a much simpler equation. It gives you the basic behavior, I would say, and which is that you neglect the space, spin, and time thing, and you take all these as scalars. And now y is my Green's function, and z is my external potential u. And all the other arguments are gone, and then you have the y0, and you have your u, and of course you have your functional derivative, which is now a simple derivative. And that is an equation that you can study, and that people have studied before us, for example, to count diagrams, but not only. But I have given you 4 of our references where we work with this equation to work out a few things of perturbation theory. I think it's very useful exercise. And for example, because you can solve the equation exactly, I will not go into this. You will find the problem of multiple solutions of different perturbation theories converging in different ways. You will find asymptotic convergence. You will find the fact that, for example, expanding in the exact screen-Coulomb interaction is not a good idea. You see heavy divergences. Expanding in RPA-like screen interactions is a much better idea. And information like that, you can get it from this very simple equations. And I think that's extremely useful. And another thing pointing forward is also that you can address another point that I think is interesting, namely, all these are perturbation theories for the Green's function, but actually what we usually do is not to approximate the Green's function. Usually we approximate the self-energy, and from this we solve the Dyson equation to get the Green's function. And you can also directly write a sort of functional differential equation for the self-energy in terms of the interacting one-body Green's function. And I gave you this equation here, so it looks quite simple. So it has an inverse Green's function, an inverse matrix, and a Coulomb interaction, but the inverse matrix contains the first derivative of the self-energy. So it's a heavily nonlinear equation. Okay, and then you find immediately that this could, in principle, create more than one functional sigma of g. And there could be problems because maybe some are correct and some are not correct. And in fact, this comes back to the problem of the domains of the Green's function. And all this I will skip it. You can explain this with these simple equations. And if you're interested in this, there is a work by Adrian Stan and others from our group, and where we have explained the findings of Evgeny Kodzek and co-workers about the problems of the Latinger-Ward functional. Again, using this very simple equation. So there are some structural problems in the perturbation theory of Green's functions, and you can explain them and find them by using simple scalar equations. And I think that is very interesting. And if in the discussion you're interested in one of these points, please ask me. Okay, I would like to focus on a last question, actually. This is why I would like some time. And this is that when we do perturbation theory, we do this around something, and in Green's functional theory, we expand around the non-interacting system, right? To be very precise, often we tune this starting model. For example, we start from a Kohn-Sham Green's function. So an independent particle Green's function, which is not really non-interacting, it has some mean field interaction built in. Okay. So the question is, how much does this help you in your convergence of perturbation theory? And of course, the dream would be that you have such a perfect starting point that you don't have to do perturbation theory at all. so that your model would replace the real system. And then you say, I don't like this. How can it be? I mean, how can I have a model that is different from the real system and it still gives me the correct Green's function? But we can again learn from density functional theory here. Okay, so density functional theory, as we have said, we have to build functionals, which we don't know. And in particular, in the Kohn-Sham strategy of density functional theory, we build an auxiliary system with an exchange correlation potential that gives us, in principle, exactly the density. We have talked about this earlier in the question. So we have we have a model system, an auxiliary system that is different from the real system, that has an effective, simple effective potential that gives us, in principle, the density. It's a dream, but we don't know this potential. Okay, so what was the first idea of Kohn and Sham? It was to say, okay, since we don't know it, we take it from somewhere else. And the only place we could take it from was the homogeneous electron gas. So the idea was to approximate this potential that is a functional of the density in principle everywhere in your system and at some point R, and to take it from the homogeneous electron gas, calculated with some density. Okay, so when you say the homogeneous electron gas, you have to specify density. So which density did Kohn and Sham take? They took the density, there was just the density at the point R where you're interested in the potential. Okay, so this is a local density approximation. Now, as a remark, you will find that this means that actually the model, the homogeneous electron gas, does not give you the exchange correlation potential, but the exchange correlation potential at every point R will come from a different homogeneous electron gas. You use a different homogeneous electron gas for every point. This is how you can use a very simple model to obtain a quantity in a real system by using actually many models, or let's say the same model, but with many different parameters in every point. So this is the LDA idea. This is good because, okay, the auxiliary system is a good idea anyway, but because the quantum Monte Carlo people have done a great job in homogeneous electron gas, so they have actually solved the exchange correlation problem in the homogeneous electron gas, have solved it once and forever, and now every time we do an LDA calculation, we use their result. We do not calculate exchange correlation, we take it. That's much more convenient. Okay, then from this starting point, you can of course expand, and people have expanded. Even Kohn and Sham have already expanded around the LDA, and we have also done some work in the past. But you could also try to do better. Many people try to do better, and this is not an exhaustive list. Better than the LDA, using the homogeneous electron gas, but doing better. Okay, in the framework of the Faraday discussions on density functional theory, we have also discussed this. So in our group, we have some work on how doing this in principle exactly, and how to find better and better approximations beyond the LDA. This is just in case you are interested in, but here we have a different problem. So as I said, we use a different model to simulate the real system in each point in the LDA. And this idea of how to use the homogeneous electron gas for DFT was actually based on Walter Kohn's concept of nearsightedness. It's really a physical idea. The physical idea is that the exchange correlation potential at a point R, which depends in principle on the density at every point in space, is completely determined by the density in the vicinity of this point. The system is nearsighted. It actually doesn't know what's happening far away. And this is why you can replace the densities far away by the same density at the point, okay? So this nearsightedness concept allowed Walter Kohn to introduce the LDA. Now the question is, could we use nearsightedness in Green's functional theory? So it would be a completely different strategy from perturbation theory. It would be closer to what we do in density functional theory. you can immediately see the problem. For example, the self-energy plays the role of the exchange correlation potential. The self-energy depends on two places in space and frequency or time difference. So if we say we are nearsighted around which point? R1, R2, the average, at which frequency or at which time difference? And note a note concerning time. We are in a static system, so it's not a question of being nearsighted in time in the sense of making adiabatic approximation. And this is still something else that you can do in a time-dependent framework, which I will not be touching upon because I think Robert will do it. Okay, so the question is, how do we use nearsightedness when we have these non-local objects? So let's look at the answer of dynamical mean field theory, or equivalently spectral density functional theory. Dynamical mean field theory, which is a people would say non-perturbative approach to approximate our Green's functions. And I tell you that dynamical mean field theory is the strict equivalent of the LDA. Why do I say this? Okay, the target in density in the Grundscham system is the density. The target in dynamical mean field theory is the local spectral function. So this is the spectral function written in a site and orbital basis in local orbitals and taking only the diagonal in the site basis. So it's the imaginary part of the diagonal of the Green's function. Okay, this is the equivalent to a local density. You can immediately see that now we don't have a problem of having two space arguments. We have only one site. And so for this reason, we can do the same. We can use nearsightedness as in the LDA. So the auxiliary potential in the Grundscham world is the exchange correlation potential. Now our auxiliary potential is a local self-energy. And note that this local self-energy is not the diagonal of the exact self-energy. You can build an in principle exact theory for the local part of the Green's function by using a local self-energy. And as a note, this is simply still another auxiliary system. It's not the Dyson, not the full Dyson equation. It's not the Grundscham equation. It's something in between. And actually, whenever you are interested in a part of the Green's function, for example, the diagonal, which is the density, or just a diagonal element, or just the imaginary part of a diagonal element, in all these cases, you can introduce an auxiliary system with an auxiliary potential, and this auxiliary potential is potentially more simple than the full self-energy. And if you're interested in this, it's work by Matteo and others and ourselves, and there is more recent thing on this here. Okay, so this local self-energy in DMFT is something like one of these auxiliary potentials. And then the question is how to get it. And here we use a model, the homogeneous electron gas in DFT. Now we will use another model. DMFT has opted for another model. This is a choice, and it's the Anderson impurity model. So the Anderson impurity model is one site embedded in some background. Okay, and so our self-energy in the Anderson impurity model depends on the Anderson impurity model Green's function, of course, and the approximation that is equivalent to the LDA is to say that we use the self-energy of the Anderson impurity model instead of the local self-energy, and we take it at some Green's function, which is actually the local Green's function, like here in the case of the gas, we take the local density. And this just gives you a single-site DMFT. So we have constructed single-site DMFT as a strict analogous to the LDA based on nearsightedness. And we could do so because the target quantity is local, like the density is local. It's just local in a basis. Okay, there is one complication, and this is that in the case of the LDA, when you come from the homogeneous electron gas, in the homogeneous electron gas, the interacting and non-interacting density are exactly the same. But in the Anderson impurity model, the interacting and non-interacting spectral functions are not the same. And so you have to decide whether what you import is the connection you make between two systems is via the non-interacting or the interacting quantity, right? And DMFT connects via the interacting spectral function. And actually, it seems to me that I have talked about this with Antoine Georges many years ago, and he said that doing it with the non-interacting one did not yield good results. It seems to me. Okay, so if you are just happy with the local spectral function, that's fine. It's like the LDA. It works great, as you know. The problem is that sometimes you are not happy to have only these diagonal elements or approximations to it. And so now you have to give up the fact that you say, I'm not interested in off-diagonal elements, or the grapes are too sour. And you have to think of what you could do. And then you can profit from the fact that for one electron, your exchange self-energy is just the density matrix divided by the distance, this Coulomb interaction. And so it just depends on the density at point R1 and the density at point R2. So it's nearsighted in a sense, in a more general sense. It just depends on the 2 points. And this has also been discussed by other people. And there's also work on, I think, by Lucia on this. So more generally, we could expect that essentially the densities at R1 and R2 are determining the self-energy at points R1 and R2. And this means that we could build models. But now you see, if the densities at these 2 points are not the same, we will need a model that is not homogeneous. Okay, so this brings us to the idea of building non-local, non-homogeneous model, and this has to be explored, and people have already worked on non-homogeneous models. Okay, and this brings me to the end. I hope it was not too long. So I have talked about or mentioned all these different points, and I have left some things for the discussion just mentioned to you in case you are interested. I think if thinking about the strategies and thinking about why we are doing things brings you to some suggestions, at least for me, brought me to some suggestions. For example, I think we could deepen the use of exact constraints in Green's functional theory. I think we could learn from DFT and focus more on the use of exact constraints, such as people in hybrid functionals are using Koopman's constraints. I think we could do this more. With the generating functional equations, we definitely can go further. We are working on this, and I think much more work is possible. Perturbation theory has a lot of problems. People are working on this. I think we even have a talk in this meeting. And especially with the advent of diagrammatic Monte Carlo, we will find more limits and more challenging things. And probably we have to learn from other communities. And concerning the use of nearsightedness, I think this is an idea that we should import in the business of Green's functions. It will need more flexible models, maybe also more flexible interactions. Maybe we could also make a link to the range-separated Coulomb interactions following Andreas Savin and co-workers. And that is essentially what I wanted to tell you as a basis of discussion. Thank you for your attention.
Thank you very much, Lucia. Thank you. Thank you. Okay, so there were some questions which were a little bit more specific that I didn't ask you during the talk, but I think now I can ask people to ask their questions. So Jean-Paul Lebrun, for example, could you ask your questions? I'm not sure I really understood it, so.
No, it was just in the beginning. Good morning, everybody. In the beginning of the talk, when you were discussing about the different functionals you were using and emphasizing on the functional of the external potential, I was wondering if it was general or just specific to the problem you are used to in chemistry and condensed matter physics. That is where you have Coulomb system. But what about self-bound system? Can you define the functional of an external potential which does not exist in the first place, and does it trigger some more issues to define this kind of functionals?
Okay, so the limits of what do we need to write it like this? Okay, we need that our observable our expectation value, is a statistical weight, statistical average, okay, over all these possible expectation values. And so this is here an equilibrium formulation, okay. So we need a formulation where the weights are given by the Hamiltonian, okay, such that I can write the thing as a trace, because when I can write the thing as a trace, since the trace is invariant, I can make the many-body wave functions of the system disappear. This is very important. I need a trace. Once the wave functions have disappeared, the only thing that is left is the Hamiltonian. And in the Hamiltonian, it is not important what kind of interaction you have, okay? It is, of course, important that up here, you have everything that defines your problem. So in this case, we have a chemical potential, we have a temperature, and then we have the ingredients of the Hamiltonian. And it's also important that you think that all ingredients of the Hamiltonian are fixed except this potential, okay? These are the conditions. If one of the conditions doesn't hold for your problem, you cannot do it like this. But for example, you can have a completely different interaction. It must just be true that this interaction is the interaction. Or you would get a functional of the external potential and the interaction. That's also possible. Okay? And of course, I try to be clear on this. I make a distinction between a functional, which just means that the expression contains enough information such that if you give this information, you can get the final result, and a variational functional, okay? Which means that if you take now this function, you minimize it, or you look for the extrema, you find some information. This is not a variational functional, of course.
Yep, okay. But then you could say also that in a, let's say in a path integral formulation of the problem, that the external potential finally is something interesting because it's coupled to density, and somewhat this is the conjugate in the Legendre transformation sense of
absolutely. I mean, I didn't talk about Legendre transform and all that stuff. Yeah, I brought this up because it has one particular point, this external potential, and this is that you know it. I mean, you think you know it if you give your system, you know the external potential, right? Whereas the density is something that you have to calculate.
So I had two additional questions, if you allow me to, Emmanuel.
Yes. Yeah, sure.
The first one is that how do you proceed when you choose your starting point? When you were discussing about perturbation theory, and one of the most important thing is the starting, the reference state you take to then design your expansion scheme. So how do you proceed when you have a degenerate system? So I mean, there's many things that just break down in this case. So do you have any personal or favorite methods to extend this kind of formalism to open shell systems?
Okay, I guess that, for example, Christian Brodeur would like to talk about this, but let me say a few things before maybe Christian would like to comment on this, and let me take the equation. Okay, so can you still see my slides or not?
Yep.
Okay, so if you take this equation, you will see that, as I said, at the end, we set this external potential to 0. And this is a limiting process. And as soon as you have degeneracies, okay, this is non-analytical, the limit. So you must decide how this thing goes to 0. And this will break your symmetry, okay? So then you can have two possibilities, of course. Either you work on how you get with this limit to 0, or you work already on the starting point here in the G0, and you say, oh no, I start from a symmetry broken configuration. And it's clear that if you want to have a simple life, you would definitely start from a symmetry broken configuration, right? If you take the very simple example of a Hubbard dimer with 1 electron, and you go to the atomic limit, okay, then if you do perturbation theory on the symmetric state, where you have half an electron here and half an electron here, it's terrible, okay? And if you take just 1 electron on one side, it's just trivially Hartree-Fock, okay? So it's clear that starting from a symmetry broken state is much easier. And people do this, for example, when you have an open shell atom, you would just take a symmetry broken state. Otherwise, you can of course make the problem larger by having a Green's function matrix with all the states, and then you would have to work in this way. For example, if you have superconductivity, you have the normal Green's function and the anomalous Green's function.
Yep. So this is exactly what we are doing also in nuclear physics, what Thomas Duguay and Vittorio Somma are doing. But then in finite size system, you know that symmetry, the breaking of symmetry are just obscured by the fluctuation of order parameters. And in the end, the symmetry has to be eventually restored. So this will be naturally done as you go further and further in the perturbative expansion. But somehow you also want at a specific order to exactly restore the symmetry, and this is also a bit of an issue here.
Yeah, that's an issue. Yeah.
And the very last question is: do you still have time?
Very quickly.
Okay. Oh, so we can skip this for another time. It's okay.
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 Thank you. Very much.
So Thomas Duguay wrote a comment about the Migdal-Galitsky formula. I guess it was connected to nuclear physics, because he said when you have three body effects in the Hamiltonian, seems like this formula is not working anymore.
That's true.
So,
that's true. Yeah.
Okay, so it's interesting. I don't know, Thomas, you want to comment more on that, or?
Well, I know Lucia is aware of this. Oh, let me put my yeah, and to be one slight complication that indeed the derivation of the formula just doesn't hold if you have a three-body operator, but it just means that you have to include some form of additional approximation to try to have a Galitsky-Colton-Sum rule-like expression for the energy as a function of the sole one-body Green's function. And okay, it happens so that we managed to derive such a approximate form, which work rather well, but it may end up being a problem in some situation because at least it's not formally exact. So it's just one additional layer of complication, but it's not. It was just a side remark.
No, it's important. Yeah, it's true that I forgot to say that what I'm telling here always has in mind the Coulomb interaction, or at least a symmetric two-body interaction. Yes.
Okay, and then, so thank you. Then we had a question from Hong Qiang, who wrote, so if we directly approximate the self-energy, how can we get the total energy?
Aha.
So
yeah, this is the same problem as you can ask in Kohn-Sham. If I approximate the exchange correlation potential, how do I get then the total energy? Well, from the exchange correlation potential, you get the density, but then you need a functional of the energy as a function of the density. Here the same, of course, we need a functional of the energy in terms of the Green's function. The self-energy will give us the Green's function, not directly the total energy.
Yeah. Okay. And then regarding this multiple solution problem that you talked briefly about, I think there's somebody called Simon. So I don't know who's Simon. So Simon, you want to ask your question, or?
Yeah. Yeah, I'm sorry that my whole name didn't show up. I'm Shimon Kos, KOS. And my question was, if the perturbation contains derivative, or actually contains the highest derivative, because it's the first derivative, whether it's a single perturbation and whether that can have, well, what are the implications of that?
I think I didn't understand you. Can you repeat your question, please?
Well, you said that if you do the perturbation theory, that you treat the term with the derivative as a perturbation.
I didn't really say this. You mean you're referring to this equation?
Yes. Uh-huh.
Okay.
And also the simplified version with just the one variable.
Okay, so I didn't want to say this is the perturbation. It's the difficult term. Okay, yeah. And so this is the one we have to approximate. And so either we iterate. If we simply iterate, so we start with this setting to 0 and iterate the equation, we get perturbation series in terms of the Coulomb interaction, because this term is multiplied with the Coulomb interaction. or we directly approximate this term, as I have done it in deriving Hartree-Fock and GW earlier. This is what I said, okay? Of course, what you could do is to write an equation where you have just already done one iteration and have the second derivative appearing. Or more generally concerning the second derivative, for example, this is just a one-body Green's function. If you're interested in the two-body Green's function, you move to an equivalent Dyson equation, which is the beta side beta equation, and you have higher order derivatives appearing, which you would then again approximate, of course.
Okay, thank you.
Okay, so Andreas Savin has been raising his hand for the last 15 minutes. So Andreas, go ahead.
My hand already hurts.
Yeah, I can imagine. Yeah.
No, Mike, it is some kind of connected to what you said about this unrepresentability problem, but for approximation. So the problem that we can construct the first order density matrix, but when we do approximations, we can do, so we take your example, LDA. We take a reference system that works fine. It works in a limited case. But then we have made a given approximation. We take a different system for which we also know how to make it exact. For example, it has a constant density gradient. But now if you want to put the two together, it's not trivial.
Okay, so you mean, suppose we have at our, someone has given us the calculations on two different model systems. One is all homogeneous electron gases, and one is all systems which have a constant density gradient.
Mm-hmm.
How could I use both? This is your point?
Yes.
Yeah, that means that I would probably, no, I've never thought about this, but I would probably have to first formulate my problem in terms of a functional, that is a functional of the density and the density gradient explicitly. And this is something that, I mean, we often do. For example, when you have a problem, people move from LDA to LSDA. What does it mean? It means that first you make a function, instead of making a function of the density, you make a function of spin up and spin down densities. Okay. You're not forced to, but you do it. And then you can separately import this information. And I think we should then write our thing as a functional of the density and the density gradient. And we should try to connect them to the two models. That's what I would try to do.
Yes, but you see, this is what you say. In this case, with the spin density, it's an easy thing to do. For the small density gradients, it's also an easy thing, relatively easy. It's not really trivial thing, but all these gradient approximations start from this idea that you have, but in general, it's easily possible that you have model systems which have some properties, but when you start putting these two together, they are not compatible. You start getting some incompatibility. So you have to imagine something.
But I would say the contrary, okay? As I said, I'm not prepared, but I would say the contrary. And that is that using model systems can avoid the use of perturbation theory. This is the good thing, because you can have important properties built in the model that you will not get from perturbation theory. Okay.
I agree with it.
So if we decide that our model has to contain a density gradient, this will be especially valuable if this density gradient is not to be seen as a perturbation, but as something that's really important and might be even big.
Yes.
So it's exactly for this kind of case that we would like to have the second model with the density gradient.
That's understood. That's your perspective, and I agree with it. But the point is, when you put two things like that, it may be not trivial.
It is not trivial.
To put two, you calculate two different model systems, but now you have to construct something which fits the two at the same time, and it's simpler than the general theory that fits everything.
I completely agree. And I'm even not sure whether I would really use the two model systems or whether I would not say maybe just one model system that has the density gradient is enough.
No,
Because it's not mandatory to use the homogeneous electron gas for a local density approximation. That's, by the way, a very interesting question, which has nothing to do with Green's functions. But if you think about it, if you say only the point where I am is important, it means that in the other points, I can put a density whatsoever, okay? Now, the question is, do we use the homogeneous electron gas because it's the easiest possibility to put the same density everywhere else? Or do we use the homogeneous electron gas because this homogeneous electron gas also has some properties, as for example, Kieron Burke would say, that are particularly good. And if I had put elsewhere another density, for example, I could put cosine density, right?
what density?
A cosine.
Yes.
Some other density, okay? Would that be as good, even better, or maybe worse? This I have no answer, okay? And the answer to this question will determine the answer to your question, in the sense that could the model with the density gradient be good also for this LDA part? I don't know, Andreas. I really don't know.
Yes. No, I can give you a simple example of my problem. You have a function of x. You can, and this function of x behaves well when x goes to infinity, so can make an expansion at infinity. Behaves well, it's a continuous function between 0 and infinity. You can make a Taylor series that exists, converges at x equals 0. You have a Taylor expansion at infinity. But now you are interested in intermediate point. You say, oh, well, I know, but they are approximants. Well, they can behave very well, badly in between. See,
can.
Yeah, yes.
Can.
So this is, I don't think it's a trivial problem. I think, and in this philosophy, I think we risk to hurt, to follow the nose on this kind of problematic.
Okay, maybe
No,
we're a little far here from the Green's functions, or does this refer to the double?
No. This is, I just wanted to give you, because you gave for the Green's function, gives a simple example, and you like functions. So I said, if you I take two models, I take something mathematical, which is easier to catch. I make an expansion in two different points.
No, I didn't want to take two models. No, I don't want to take two models. I want to take one non-homogeneous model. This is not the same.
No, but the point is, if you change from model 1 to model 2, it's fine, because
absolutely.
But you have more information and you want to use more information. And then how to put these two things together? And I don't think we have a general scheme to do such a thing.
No, we have to work on it.
Okay.
We have two weapons, and well, just there are people who fight with have a sword on the right and a dagger on the left, and people who can and people who cannot.
So, is this the conclusion? We have to work. I'm sorry, Andreas, because
no, it's fine. No, it's fine.
It's okay. Yeah. Okay. So just because Thomas Baker was raising his hand for the last half an hour, and then he gave up basically. So
well, I think we're out of time, so I didn't want to.
No, okay, because we started a bit late, so it's okay. We still have some minutes more. So go ahead.
Oh well, it's a very simple question. I know that reduced density, or the density matrix formulations of the functional theory, they often have it's not so easy to make approximations. We have all these wonderful approximations for density functional theory, but it's not so easy there. The other thing that I know about this Luttinger-Ward functional that you showed is that there can be bifurcations in the solution. So depending on your starting point, you might wind up at a different point.
This is actually this slide. Let me see, which I didn't talk about. This is a bifurcation of the Luttinger-Ward functional Exactly, and you get it from this simple differential equation already.
Yeah, exactly. Yeah. But so I guess my question is, because I don't really have experience with this, is there a sort of a simple way to see why this would be more useful, or maybe in these Faraday lectures that was mentioned, why this would be more useful than competitor techniques for getting excitations like time-dependent density functional theory or some other method? Or
okay, can you specify what you mean by this? Why is what more useful? Green's function?
Why sort of investigating these Green's function techniques? If I were to propose an approximation, there must be problems with it. But
Yes.
Do you see some obvious advantage over other techniques that we currently have, such as time-dependent methods? Or
I think it's okay. Honestly, I think for the moment we do not have clear evidence that building the energy as a functional of the one-body Green's function is superior to building the energy as a function of the density, for example. Okay.
Okay.
But we are not only interested in the energy.
Okay.
Many of us are interested in spectra.
Mm-hmm.
And the fact that you can write the spectral function as an explicit functional and very simple functional of the one-body Green's function, and I will come back to this if I find it. Okay, I don't find it, but yeah, here it is. Okay. The spectral function is a very simple explicit function of the one-body Green's function.
Mm-hmm.
And this, for me, is the deep reason why it's so good to find the one-body Green's function. Because you want this observable. Try to write the spectral function as a functional of the one-body density matrix.
Mm-hmm. Yeah.
We'll talk again in like 10 years or so, maybe.
Right.
I think this is the deep reason.
Okay.
Hmm.
But you could also try and compute methods with excitations. What is the sort of the
okay? So if you since you talked about time-dependent density functional theory, which is of course not for electron addition and removal, but for neutral excitations.
Mm-hmm. Yeah.
So now we have two competing methods. It would be time-dependent density functional theory, as you say, and it would be the Bethe-Salpeter equation, so the Dyson equation for the two-body Green's function.
Okay.
And we are using both. So the time-dependent density functional theory is computationally simpler, provided that you have simple approximations to the functionals. And we do have simple approximations to the functionals, simply they are not good enough to give us some of the things we would like to have, especially in extended systems, and these are especially excitons. So the functionals that we have very complicated functionals that are computationally more expensive than the Bethe-Salpeter equation that can give you excitons in TDDFT. And we have relatively simple approximations to the Bethe-Salpeter equations that do well. So since we are completely pragmatic people, we use the thing that works best.
Okay.
If you look at simple small systems, TDDFT is often winning, then we use TDDFT. Okay.
Thank you.
Okay, so and then there was a question by Tommaso Chiarotti. So yeah, Tommaso, if you want to ask your question, yeah, go ahead.
So my question
very
is
quickly.
Yeah, so I'm very doubtful on the fact that it's an extremum condition. The fact that the Klein functional is the Klein function is variational. The fact that it's an extremum and not a minimum, I'm very doubtful. I'm very doubtful because maybe for the Klein is true, but for the Lattinger word, first I don't know. I mean, when I read the article of Lattinger, it was clear that it was a maximum, and then actually, if it were an extremum and a saddle point, let's say, I would say that the question was, do you find it strange? Because I mean, if you have a saddle point, then if you do a perturbation on the saddle points, let's talk about perturbation, the interaction, for example. So electrons do not interact with E squared; they interact with you put your solid in a medium or something. The function would go completely off if it was a saddle point and not a minimum. So so my question is, do you find it strange that it's an extremum and not a minimum, and is there actual proof of it?
Okay, yeah. I try to be careful I wrote not shown to be a minimum. Okay. So what do I know? I know that we can use this extremum condition to get the self-energy. This is independent of what kind of extremum it is. It just means a derivative is 0, okay? And I've written not shown to be a minimum because I'm not aware of any proof that shows that this is a minimum, okay? I think I said, or I wanted to say it could be a saddle point, it could also be a maximum, but I don't think it has been shown to be a minimum. Maybe someone here is aware of a proof.
Actually, what I read, it was in the Lattinger paper. It was at the Lattinger word paper. It was that it's a maximum. So of course, it's just a problem of sign.
But that's the Lattinger word functional. It's not the same functional, right?
No, of course. I mean, okay, I'm confusing stuff. So let's like, I mean, the Lattinger word maybe is the true function. I don't know, but the fact that it's not a minimum. I mean, to me, if in reality something is not a minimum, you know, just a small perturbation would make a material go crazy in some sense. So maybe it's true that the Klein functional, so function of Green's function, you need to have another variable, the self-energy, I don't know. But so the fact that it's not a minimum, I mean, the fact that there is no, you know, very fundamental theory that governs a functional theory that governs a solid or a molecule, I don't know, to me it's very strange, let's say. Yes.
Okay, first of all, let me insist again. I didn't say it's not a minimum. I say I have no proof. It's not the same, okay?
Yes.
Then you can, of course, say, but it would be much better if it's a minimum. And I would, in a way, agree. Yes. I mean, I have a little bit this trouble in the sense that since the functional of the wave function is has a minimum, there should be a way to construct also a Green's functional that is clearly as a minimum, okay? If you put all the information in the best possible way, okay? But I didn't work on it, and I am not aware of the solution, so that's what I can say, okay? But maybe someone here, and maybe Robert will comment on it in his talk or so. Let me just, if we don't know something, we don't have a proof, it has not shown to be a minimum. Okay.
Okay. Thank you very much. So now we've been talking for 1 hour and a half, perfect timing. So thank you, Lucia, very much. It was very nice to discuss and have such an overview. So so I think we can thank the speaker and all the people who asked questions. So now we have a break. And so we should meet again at 4. Yeah, so now it's coffee break. Okay, so see you in 20 minutes.
See you.
See you.